So, in 15.3, last time we were talking about conservative vector fields, and we gave this, or stated the fundamental theorem of line integrals, which was really useful and an easy way to compute line integrals. And then we kind of alluded to how we're going to check to see if a vector field is in fact conservative. But let's look at this. So, all right, I'm going to write it this way. So, this is another one of these things where we'll state it. We need the idea of simply connected to state this thing properly, but it doesn't affect us very often. Okay? All right. So this is a concept. So the definition, again, I'm not even going to put definition down because this really isn't a definition. It's more of a vague idea. So we're talking about regions in the plane. There's a region in the plane, and this region is considered simply connected. If you took any, I say loop, if you took any circle like this, right, you can imagine you could compress that circle into a point, right? So we can collapse that circle into nothing. No matter where you draw a circle, you should be able to collapse that into nothing. I really should have. I'm going to draw my circles in another color. So you can collapse that into nothing, you can collapse that into nothing. Does that make sense? So this is what we mean by simply connected. Okay, and that's different than this region where I've drawn some holes in it. Okay, so now the region is everything inside the big circle or big blob and outside those circles. Does that make sense? And so this is not simply connected, and I'll show you what I mean by that. So not simply connected. So we can draw plenty of circles here that we're able to collapse, right? But if you put a circle around that guy, there's no way to collapse it and stay within your region. Does that make sense? So that's the concept of simply connected, and I think that's probably all we need to really know. I'll say not connected. Just means something like this, right? We have different pieces of it that you really can't get to. So again, remember we talked a little bit about connected last time, and we said a region was connected if you could get from any point to another by a path that stayed inside of there. And there's other terminology where the line has, so, well, I'm not even going to get into it. And so we can say this, we can do the same thing for three-dimensional structures. Again, right, a box. I have no idea why I'm picking the sides I'm drawing. A box will be connected, but a torus, which is I should say simply connected, but that won't be, right? You can imagine putting a circle around the ring of it, right? There's no way you'll be able to shrink it down to nothing. So three-dimensional ones, again, it's not going to be, most of the time we're going to be, well, I should say, most of the time we're not even going to think about this idea, but it's all sitting in the background. So this just allows us to state our theorem, which is what we want. So suppose that F is a vector field in R cubed, and we'll allow R squared. So again, R cubed just means a three-dimensional vector field, right? With component functions that have continuous first derivatives. First order derivatives. And again, the formal statement of this isn't something that you should get too bogged down with. On a simply connected, region D, okay, and then F is conservative if and only if the curl of F is 0. So remember, we saw last time that if you're conservative, your curl is 0. So this theorem is just proving the other direction. And so that simply connected comes in that you can come up with these weird counterexamples where this isn't true. But let's not. We're not gonna see those things, I guess is my point. So, and I'll just say note in R2 we replace, so this same theorem, but we replace the curl of F being 0 with, so in this case we're going to assume we got this P Q. Right, so we replace it with the Q sub X equals P sub Y. And so those are your tests for whether something's conservative or not. So from now on, if I ask you if something's conservative, the easiest thing, right, if it's a two-dimensional vector, just do check if P sub Y equals Q sub X. And if it's 3, it's in 3 space, then check the curl. Okay? So let's do an example. Show that this one will be pretty easy, I think. You can probably even guess the answer. Is conservative. And I'm just going to say this, using the curl. So remember, we did some examples before where we showed something was conservative by simply demonstrating that we could come up with a potential function. Most of the time when I want you to check it, I'd like you to use the curl or use the piece of y, q sub x. Okay, so show it's conservative using the curl, and then find a potential function. And let's just do this. I want to do more than one of these with the same direction, so let me just call this one A, and then I'll state another function here, B. So, try this one for a minute. Oh, and I guess for the second one, I did say, using the curl. For the second one, don't use the curl, use the piece of y, q sub x. Okay, so let's just go through this again. It's been a little while. Curl. Alright, operators. Hopefully I wrote this one down right. Easy to make some mistakes here. Okay, so what do we get? With respect to y, we get 12 x squared y squared z cubed, right? And then minus with respect to z, 12 x squared y squared z cubed. So you get 0. I mean, you should. I'm telling you it's 0, right? Because I'm telling you this is there, but let's just make sure. Again, the middle term, this way you get 8x y cubed z cubed, 8 x y cubed z cubed minus that, so that's also 0. I mean negative 0, but it's still 0. And then finally, you can double check that the last one is 0 as well, right? So, I mean, I don't know that you have to show a whole lot of work. Should indicate you understand what the curl looks like and be careful with it. I mean, you know it's going to be 0.
I think the last one is not 0.
Isn't it? Should be 0 if we, unless we screw this up. So it should be 6 x y squared z to the 4th, and then, yeah, 6 x y squared z to the 4th. Now be careful. A lot of times the directions will say, you know, determine if this is conservative or not, and so you should show the curl and then go from there. Okay, so now, so it is conservative, so f equals the gradient of some little f, right? And so now we want to find that little f. How do we start? F sub x is 2x y cubed z to the 4th. So what's f? X squared z to the 4th, and then possibly plus some g of yz. In this case, you probably could almost stop here, right? Because if you see that f, what is the derivative with respect to y? 3 x squared y squared z to the 4th, and with respect to z, 4 x squared y cubed z cubed, right? So you're done. You have a potential function. Maybe I'll leave it at that. So sort of by inspection, you can see that works, right? But be careful. A lot of times you're going to have to come back and do some extra work. Does that make sense, though? So you see, once you can find a potential f there, or a candidate for f, and it's got that plus some constant at the end. If you realize that constant doesn't need to be there, you can just stop. You say you're in good shape. Okay. So for this one, again, let's call that P and Q. And again, the test for conservative for a two-dimensional vector field is to check the Py and the Qx, right? So Py is what? Cubed y cubed, and the Qx turns out to be the same thing, right? And so it's conservative. So F is conservative. And notice, I haven't said anything about the regions that these were over. These are both defined over everything. But for the most part, we just look at their domains, and it's unusual to find a function whose domain isn't simply connected. And even if it isn't, as long as you're trying to do something on a small region, you should be okay. All right, so it's conservative, so now find your f. And so again, 2x cubed y to the fourth plus x, so this time what's f?
X to the fourth over 2.
Okay, so that'll give us x to the fourth, y to the fourth over 2, right? 4 canceling, and then plus x squared over 2, right? Maybe I'll just write it like this. Okay. All right, and then plus, in this case, just a g of y, right? And notice this time, if you ignored the g of y, you don't get what you want, right? You get this first part, okay, but you're not getting the y that you need. So let's just follow our steps. F sub y is 2x to the fourth y cubed plus 0, right? Squared is nothing, and then plus g prime of y. And so again, that's the right first bit, but we're missing the y, so our g prime of y must be y, so g of y is y squared over 2. And so your potential function f is just x to the fourth, y to the fourth, right, plus x squared, and then plus y squared over 2. So just put all of that stuff over 2. Make sense? Okay. So let's come back and do another one, but as long as I have that one up here, let's do an integral using that one. Let's see. So for the previous capital F, I guess I'll just write it out, 2 with an x cubed y to the fourth plus x, 2x to the fourth, y cubed plus y. Find the integral of f dot dr, where this curve is just given by this guy. T is cosine of pi t minus 1, comma, sine of pi t over 2, and we go from 0 to 1. So, try to compute that line integral and see what you get. So, this should be incredibly easy. If you tried to just use the definition, right? that we saw before of F dot dr and calculated actually the derivative of this mess,
Of the magnitude.
and then plugged those into here, right? But you don't even need the magnitude, right? It's really just r prime dotted with that F. This would become a big mess to try to evaluate, right? But since this is a conservative vector field, what do we know? That the fundamental theorem of line integrals says you can just take your potential function, right? And then your at r of your endpoint minus your potential function at r of your starting point. Right? So I hope one of you tried to do it the long way and saw that it was messy. Did you not?
No.
Darn it. But again, don't forget, we have this nice tool now, right? And so this one should be now, what's f of, what's r of 1? Of 1 in for t, what do you get? -2. And then 1. Good. And then you plug 0 in and you get -1, right? 0 minus 1. Got the 0 from there. And then 0, right? Is that okay? Yeah, so it's cosine of 0 will be 1, but there's a t in front of it. And then that's just a matter of plugging into our f, right, which we evaluated over there, so then it's just, what is it, to the 4th and the 4th? So -2 4th, 1 to the 4th, plus -2 squared plus 1 squared over 2 minus, well, there's 0, so the only term that shows up is the x, right? So it'll be -1 squared over 2. And so you can clean that up. That'll be a nice reasonable number, right? You're gonna have 1 and 1 here will cancel, and so you'll get what, 16. I guess I'm just doing it now. 10, I guess, for your final. Double check that you're getting 10. And you add that up. Is that okay?
Yep.
Be careful with signs, right, when we do this. But anyways, this is right, a pretty powerful thing that this can do all kinds of stuff. You can make really messy line integrals quite easy after you use that. Okay, the next. So, determine if all right. Okay, so you got a giant mess of a function there. Determine if it's conservative. If it is, find here, let's, actually, I don't. I wanted one that was, this one is not.
Can we make it easily conservative?
Log x squared. So we just, okay, let's throw an x in here, I think that does it. I wrote it down. I guess I gotta check the last one too. Okay, so. Any thoughts?
I still not very concerned.
I think your problem's where you added the x when you,
It's 6x squared.
Yeah.
And the other one's 12x.
Oh, wait, yeah, the other one is.
And there is a y squared to the z
My
for
goodness.
the other one too.
I think if you would have made the 6 a 3, you would have been okay.
Yeah, that's probably true.
How are you paying that close of attention? Does this do it?
But the second one is still just negative y squared e to the z. Because pz is 0 and rx is,
Alright,
oh no, wait,
I think it's
I found
I
it.
think it's okay now.
That's right, that's right.
I think this is okay now.
Yeah, that's right. Sorry.
That's right. I had this.
Well, I think the original was, yeah, it would have been 6Z. 6Z. Oh, it didn't have it. Oh, no, the X is gone. I think the other one, the original one was okay, wasn't it?
Probably, because the x to the first would just.
Alright, we're going back to the original. All over the place today. It's okay. Minus 6x z squared. That's why don't just do things in your head. It's easy to confuse yourself. So let's do the curl here, as long as there was so much confusion. Sometimes you'll just write this. If you don't want to write the partial derivatives, just to keep track, you can use d sub whatever. So, I guess I'm going to need a lot more space for this one. Let me just write them up. 2x cosine y minus 2z cubed. If it's not conservative, we'll just give up. Go home. Okay. So, let's go through this and just confirm. So, when you do with respect to y, you're going to get what? Just 2y e to the z, right? And then minus, with respect to z, just 2y e to the z. So the first one's definitely going to be 0. And then the middle one will be negative, but let's hope we get 0. If we do the derivative with respect to x, what do we get?
-6.
-6 z squared. And then if you go back the other way, right, it's the same thing. So you do get 0 there. And then finally, the last one, with respect to x, you just get what, 2x sine of y. And then when you go back the other way, it'll be negative 2x sine of y. And then it'll be the same thing there. Okay. So, conservative. Now let's set about finding the potential function. And this one's just a little messier than the earlier ones, right? So we'll just start off with our f sub x being what? That first component, what is it, 2x cosine of y minus 2z cubed. Now, this is another place where you might realize, right, so it's not going to be all that complicated. Essentially, right, when you take the derivatives here, you're not going to get this piece or this piece, and so you'll have to incorporate those back in. So there's other ways you could sort of work around this, and I don't know. You might save time, but I think it's more likely you'll screw something up. So let's just take our time. So with respect to x, what do we get?
X squared.
X squared cosine y minus
2z.
2x cubed, and then some function of y and z, right? Take the derivative now with respect to y. Again, the order that I'm picking x, y, z, it doesn't matter. You could do any order you want. But when we take the derivative of this, we should get
Minus x squared.
negative x
Sine.
squared.
Sine 1.
Sine.
Oops, sorry. 0, right? And then g sub y, right? I'll just leave it like that. And so what should g sub y equal then? So it needs to be the middle term, right? We have the negative x squared sine of y, but we don't have any of the other bits. So the g sub y should be 3 plus 2y e to the z. Is that okay? And now pull back to g, so now integrate with respect to y. G should be 3y plus y squared e to the z. So that goes back in for your g, and then plus, I'm going to write h of z, right? Some function of z that we don't know about. And so that goes back in here, and so I'll just rewrite our f. So our total f so far is x squared cosine y minus 2x z cubed plus 3y plus y squared e to the z plus some unknown function of z, right? And then at this stage, you might be able to guess what the which the h is, but let's just work our way through it. So f sub z, negative 6x z squared plus y squared e to the z plus h prime of z. And so we have everything except for the 7, right, over there. So the h prime is 7. Of z is 7. So z, or h is 7z. So then you're done. Your f is this whole mess we have here. Plus 7z. All right. Does that make sense? So the whole point being that, right, if you can show it's conservative, then computing these integrals will be really easy. All right, so I think that does it for 15.3. We'll move into 15.4. 15.4, we'll talk about how we can compute these line integrals in a different way using double integrals instead.